Hello, and welcome to my video series of algorithms. This is part 5 of Module 5, Divide and Conquer Algorithms. In this video, we will be discussing the integer multiplication problem. The integer multiplication problem involves computing the product of two integers. When the integers are small, their product can be computed directly in constant time without causing overflow. However, when dealing with larger integers, computing their product directly may lead to overflow, resulting in incorrect outcomes. To tackle this problem, we can use the traditional standard algorithm, which no longer runs in constant time. For example, consider the multiplication of two integers, 1,200 and 3,612. The standard algorithm multiplies the integers digit by digit, shifts the intermediate products according to their significance, and then adds them together. During this process, every digit in the first integer is multiplied by every digit in the second integer. If we assume that there are n digits in each integer, the time complexity of the standard algorithm becomes O(n squared). If the two integers have different numbers of digits, we can pad the smaller integer with zeros at the front to make both integers the same length. Therefore, in the rest of this video, we will assume that both integers have the same number of digits, n. Since multiplication is a common operation that may be performed frequently, it is crucial to make it as efficient as possible. In this video, we will present a divide and conquer algorithm that improves the O(n squared) time complexity for integer multiplication. First, let's develop a naive divide and conquer algorithm for the integer multiplication problem. Recall that the input size of the problem is determined by the number of digits in each integer. Thus, we will create smaller subproblems using subsets of digits in the integers. Following the intuition, we will partition each integer into two halves. The first half contains the most significant digits, while the second contains the least significant digits. For example, given the integer 1,200, we can divide it into two halves. 1, 2, the most significant digits, and 0, 0, the least significant digits. Similarly, for 3,612, we divide it into 3, 6 and 1, 2. As the right figure shows, we now need to compute the product of 1, 2 and 0, 0, 1, 2 and 1, 2, 0, 0 and 3, 6, as well as 1, 2 and 3, 6. We can then sum up their products and obtain the final result. In this case, the original multiplication problem is divided into four subproblems, and computing the sum of the intermediate products corresponds to the merge step. More formally, we can generalize the idea as follows. Given two integers, x and y, each with n digits, we can write x as x0 times 10 to the power of n over 2 plus x1, where x0 corresponds to the most significant half of digits in x, and x1 corresponds to the least significant half of digits. Similarly, we can write y as y0 times 10 to the power of n over 2 plus y1. We then compute the product x times y as x0 times y0 times 10 to the power of n plus x0 times y1 plus x1 times y0 times 10 to the power of n over 2 plus x1 times y1. To determine if the divide and conquer algorithm can improve time complexity, we can check whether it saves computation compared to the direct solution. In a direct solution, we perform n times n or n squared single-digit multiplications. With divide and conquer, x0, x1, y0, and y1 each contains n over 2 digits. Thus, computing the product x0 times y0 requires n over 2 times n over 2, or n squared over 4 single-digit multiplications. The same applies to the products x0 times y1, x1 times y0, and x1 times y1. Adding this up, the divide and conquer strategy also requires n squared single-digit multiplications, the same as the direct solution. Therefore, the naive divide and conquer approach does not save computation. To optimize the divide and conquer approach, consider how the product x times y can be computed. Observe that we do not need to compute the actual values for x0 times y1 and y0 times x1. Knowing their sum is sufficient to compute x times y. So, how can we determine their sum without knowing the individual values? We turn to the equation highlighted by red in the slide. Specifically, the sum x0 times y1 plus x1 times y0 can be computed as x0 plus x1 times y0 plus y1 minus x0 times y0 minus x1 times y1. This way, we only need 3 multiplications: x0 plus x1 times y0 plus y1, x0 times y0, and x1 times y1. This reduces the number of subproblems from 4 to 3. Note that in the first product, x0 plus x1 times y0 plus y1, the two integers x0 plus x1 and y0 plus y1 can each contain at most n over 2 plus 1 digits, which is approximately n over 2 digits when n gets large. Therefore, we can say that all 3 subproblems have a size of n over 2. This smarter divide and conquer algorithm saves computation by reducing the number of subproblems from 4 to 3. While we need to perform several additional additions and subtractions, these operations can be executed in linear time and are much more efficient than the O(n) squared multiplication. Here is the pseudocode for the divide and conquer algorithm for integer multiplication. Lines 5, 6, and 8 correspond to the 3 subproblems where recursive calls are involved. The other steps can all be completed in linear time. We can leverage the master theorem introduced in the previous video to analyze the time complexity of this algorithm. Here, each larger problem is reduced into 3 subproblems, so A is 3. The size of each subproblem is reduced to half of the original problem, so B is 2. Finally, the divide and merge steps can be finished in linear time, so C is 1. Given their values, we have C is less than log BA. This corresponds to the first case of the master theorem. As a result, the time complexity of this algorithm is O(n) to the power of log BA. Plugging in the values for A and B, we find that the resulting time complexity is O(n) to the power of 1.59, which is faster than the original O(n) squared time complexity. Note that we can achieve even better time complexities for the integer multiplication problem. For example, using a similar approach, the Thum-Cook algorithm divides the integers into 3 equal-sized portions, each containing n over 3 digits. Then, it shows how to compute the final result using only 5 subproblems. According to the master theorem, its time complexity becomes O(n) to the power of 1.46. If you're interested, please refer to the corresponding materials online for more details. Thank you very much, and see you next time.